So our next speaker is Professor Srini Parthasarathy. He's a professor of computer science and engineering and the director of the data mining research lab at Ohio State. His research interests span data analytics, databases, and high performance computing. He's among a handful of researchers who have got both the DOE and NSF Career Awards. He and his students have won almost 10 plus best paper awards uh, in a lot of conferences, the WebConf, SIAM data mining, CKDD, VLDB, ISMB, ICDM, and ACM Bioinformatics. He has chaired the SIAM Data Mining Conference Steering Committee till 2019, and also serves on the editorial board of a lot of journals. So since 2012, he also helped to lead the creation of OSU's first of a kind nationwide undergraduate major in data analytics and serves as one of its founding directors. So today he will be talking about stochastic flow clustering, consolidation, renewed bearing, and applications to image segmentation. So Srini, welcome. Please share your slides and you can get started. Uh, Srini, we cannot hear you. Srini, yeah, check your microphone.
Can you hear me now?
Yes, yes, yes.
Okay. Yeah. Yes. Thank you for the invitation and the introduction, TK, Anil, Raghu, Lee, and all. So let me just start by sharing my screen and hopefully we can get started. So can you see my slide now?
Yes, yes,
Okay,
yes.
excellent. So what I'm going to be talking about, I'm going to take a little slightly deeper dive into some of the algorithms that we have been looking at that sort of facilitate some of the interactions that both Raghu and Eric just spoke about. A little bit about me. My background is in analytics and machine learning. I do work in database systems, and oftentimes convergence of these things end up looking at high performance computing solutions to this. The talk today, I'm just going to focus on the first part of it, and so I'll be talking about this problem that a lot of us are interested in, and that has wide applications from a number of different disciplines. In fact, this is some of the work that I'm going to be talking about is in collaboration with chip manufacturers like Intel, in collaboration with crisis volunteers around the world for flood mapping, and works on really large graph structures, essentially. And I'll try to make the connection between, again, as Eric said, and I will repeat, uh, I don't have much of a background in pathology, but have been engaged in some of these interesting discussions. So I'm very interested to learn, some of the nuances of some of the different things. So the last couple of days have been, wonderful. So the problem I'm going to focus on in this talk is succinctly stated as follows. Given a graph, how can we discover groups of nodes that are strongly connected to one another, but weakly connected to the rest of the graph? And subsequently, I will try to make the connection between this and the kind of segmentation that Raghu alluded to in his talk, and several others have talked about, including Ulysses yesterday in yesterday morning's keynote. So that's sort of the baseline that we're going to be looking at. And in particular, I'm going to talk about this, very interesting idea that was proposed as part of a PhD thesis in the Netherlands by Stijn van Dongen. And what we're going to talk about is, what the basic idea of this algorithm is, and what are some of the limitations of the original algorithm, and how we've sort of overcome some of those limitations over the course of several years. Now, at a high level, this pictorial tries to illustrate the basic processing of what we're trying to do, which is finding these clusters within graphs. And the way it does this algorithm works intuitively is that it stimulates a series, hundreds of millions of random walks, and uses the information from those random walks to isolate and identify clusters in the graph. And so that's the process. It starts by initiating these random walks as you go from left to right and from top to bottom. And eventually, over time, things start converging, and you're left with a fairly sparse structure that represents community structure within this particular graph on which this algorithm is going to operate. So just to sort of make sure that everybody is on the same page here, what I've illustrated in this graph is a simple graph of 4 nodes. There are 4 edges in this graph plus self edges, which are illustrated in blue. And the operations in this particular algorithm operates on a matrix like the one you see on the right, where the columns essentially can be thought of as probability distribution. They sum up to 1. So this is what is called a column stochastic matrix. And again, I'm not going to dive into the details of the algorithm, but I want to make sure everybody understands sort of, the fact that we are dealing with sparse matrices in these kinds of problems, because the graphs themselves often have a certain sparse structure to them. So the algorithm proceeds through a sequence of steps, certain operations where these random walks are being simulated, and until convergence. And at convergence, you have these extremely sparse matrices that can then subsequently be interpreted as a clustering and can be fed back to the algorithm as, here are the clusters for this particular graph. And again, as I said, I will connect this to image segmentation in a few slides. So the overall procedure here is a sequence of steps, as I said. But here, what I'm trying to provide here is some intuition as to what each of these steps involve. So again, the first step tries to enhance flow to well-connected nodes. These are sort of core central elements in the graph that sort of form the core of different communities. Additional steps in the random flow simulation, in the random walk simulation, attempt to sort of provide a loosely a mechanism that sort of ensures that things converge to nice solutions by ensuring that these transient distributions get the rich get richer and the poor get poorer through an inflate operation. And then there are some other steps until the final clustering is interpreted. But again, I'm not going to go into the details here, but this is the basic approach. And in a pictorial sense, this is what this random walk simulation will look like. It first starts by, these random walks generate, increases the density in some senses of the connections. And then over time, as some of these other operations are playing a role, like inflation and pruning, you start seeing very sparse structures that can then be interpreted as these kind of clusters that you want to focus on. So this is, at a very high level, the original MCL algorithm. As I said, von Dongen is a bioinformatician now, got his degree in applied math. This is a very theoretically well-founded algorithm, and it uses, particularly exciting from the HPC standpoint, it uses basic linear algebraic operations that we know how to scale quite nicely. And it is particularly effective against noise, certain types of noisy behavior that you do see in other algorithms. So what we have done through a systematic benchmarking of the algorithm, not just us, but others as well, noticed that there are some limitations with this. And we've attempted to try to redress some of these limitations by making small tweaks to the algorithm. And so one of the solutions we come up with, you probably, if you listen to the first talk given by Ulysses, he talked about, different parameters and, the need to regularize. And Raghu also talked about this in his talk earlier today. So what we found was that one way to correct some of these problems is to do a better job of regularizing, because these columns can be interpreted as probability distributions. So that's one solution to that problem. And to the scalability problem, we came up with an effective way of scaling this, not just on a single node, but across a distributed system as well. So again, I'm not going to go into the details of the formula and things like that, but if you interpret each of these columns as a probability distribution, one way to ensure that, this microclustering of the behavior does not materialize is to regularize and ensure that neighboring flows are constrained by how neighbors are flowing as well, how neighboring nodes are flowing as well. And so one way to do this is to use a well-established metric like the KL divergence, a well-known measure for comparing probability distribution. And it turns out to have a beautiful closed form solution that we can simply plug in to the existing algorithm. So we just replace M star M with M star MG, which is this closed form solution that we can find. And the algorithm just works fine, and it eliminates that microclustering or microsegmentation problem that shows up. The other sort of idea that we explored here, again in the single node context, is how we can take lessons learned from other sort of graph clustering approaches that have existed in the literature and bring it to bear on these kind of stochastic flow algorithms. And so the basic idea is that you take you have the original graph is quite large. You take a sequence of steps to essentially compress it in a way that captures the global topology of the graph. Then you operate on this compressed or coarse representation, and then you have a sequence of refinement steps that takes it back to the original sort of graph. Now, the advantage of something like this is that at its compressed or coarsest representation, things fit quite nicely in L1 cache, as close as possible to the processor. So you're saving a lot of effort and time in terms of dealing with the scales of images or the scales of graphs that these kind of problems can work on. And so it's an effective sort of high performance computing abstraction that finds a lot of use in these kinds of problems. So we found a nice solution to this problem for this particular type of algorithm. So those are some scalability related solutions. We did other things that we have looked at in this context that I'm not going to discuss, including mechanisms to sparsify the original graph even further without impacting the output. And we have some results in theoretical rationale for this. And then together with some colleagues and students, we've been examining ways in which this algorithm can also be accelerated in a parallel system, including hybrid CPU, GPU kinds of systems. And you'll hear more about those kinds of ideas from some of the talks tomorrow and some of the talks that are coming through. So now what I'm going to do is I'm going to take a quick change sort of focus a little bit and try to connect what I've described so far in terms of some of these ideas for stochastic flow clustering and try to illustrate how we've used these kinds of things for image segmentation problems that arise in public health crises, especially for things like hurricane-induced flooding and so on and so forth. So again, floods are the #1 natural disaster in the world, in the United States as well. And depending on how you evaluate these things, and again, there are different ways, but this is certainly something that is important. We have the challenge of being able to process and distinguish sort of these flooded areas from non-flooded areas. It's not always a binary problem. There are different classes of types of flooding and things like that, that remote sensing and flood mapping and GIS folks focus on. But it's very useful when, in terms of guiding first response resources in these kind of emergent situations. So assessing flood risk, it's also useful for mitigation and assessing future flood risk in certain areas. The reason I bring this to your attention is because we have to deal with problems that are similar to some of the problems that Raghu described, that others yesterday described, in terms of the differential sizes and arbitrary shapes that we have to capture. Again, like what we've heard from some of the pathology folks, fully automated methods work up to a point, but are not enough. Domain guidance, having a human in the loop, as Eric just talked about, can redress, but there are two sort of important things that we have to deal with here. And as I understand it, this is also an issue in sort of pathology in general. You don't always have the right expert available at the right time. They're not always available, and also it's a fairly time-consuming process. And you need real detailed experts to help out with this. So how can automated tools and this kind of human machine teaming help sort of bridge the gap? And in terms of the size and scales of images, we require, I mean, again, we are dealing with tens to millions, almost up to a billion node graphs in these kinds of problems, or billion pixel images in these kinds of problems. This number here on the slide is somewhat dated. So what are we dealing with? So let me give you a pictorial example. So this is a flooding that occurred in the city, southeastern city in India called Chennai. It's my hometown. It was a major disaster in about 4 years ago. And this is basically giving you a pictorial representation of what things look like both before the first depression. There was a sequence of 3 depressions that hit the city. So it was not just one sort of cyclonic event. It was a catastrophe that sort of happened because multiple things, all somewhat rare, happened together. So it was like the first time in 400 years that the city had faced anything like this. So what you're looking at is, as you can see in these kinds of images, you can see that the dark black is sort of the water areas. What you see on the right is sort of the coastline. Chennai sits on, on the Bay of Bengal, it is internally it has these large water bodies that you see after the cyclonic event. So it was massive flooding, and this is just one example of the kinds of things look like in this particular city at that particular time. So again, just like pathologists, we have in these kinds of situations, you have sort of this drill down and roll up that you have to constantly do in order to exactly and precisely characterize what types of flooding, where, and where to prioritize and things like that. So it has some high level similarities to some of the problems that we've heard from the other talks. So in this kind of problem, where does the graph come into the picture? And so a very popular, and I dare say perhaps the most commonly used approach for image segmentation involves converting the problem first to a graph, and then solving essentially a graph clustering problem that can then be portrayed back to the image segmentation problem. So this is a style of work initiated initially by Shi and Malik in a landmark paper on spectral segmentation back in 1999. But then subsequently, there have been improvements on this. So essentially, what one ends up doing is you treat each pixel as an image in a node, and you devise a mechanism for determining whether there's an edge between 2 pixels or 2 nodes, depending on how similar they are in terms of texture, color, or additional features, and also how close they are in terms of physical distances. And there are some regularization steps that people use. The math is not important. Essentially, they treat the problem by converting it to a graph and then treating it as a graph clustering problem that can then be given back eventually to an image. So how does MLR-MCL or the stochastic flow clustering algorithm that I was describing fit into something like this? So what I'm showing you here is an image of a flood that occurred in Houston. And what I'm showing you here is a blown up part of one part of this image on the right. And it shows you the kind of patchwork that something like MLR-MCL will give you. That is, it groups together lots of these pixels into these clusters. And then one can employ a simple form of computational patch stitching to identify these kind of irregular shapes that can precisely characterize the type of flooding that is happening in a way that's better than what was the state of the art before we came up with this particular approach. And so this just illustrates the difficulty of the problem as well, because oftentimes when you're taking these images, these are satellite images or flyover images. You have multiple resolutions you're dealing with. You have to be able to fuse information from multiple sources. There are multiple features involved in these kinds of efforts. And so it is quite a challenging problem. And so something like, these stochastic flow clustering algorithms can give you really nice results in terms of segmenting out some of these things. Now, we haven't tried it out, but as Raghu alluded to, these kind of track-like patterns that show up in the pathology example could be an example of something that, an idea like this could be potentially used for. Now, in this particular case, we had an expert spend the better part of 2.5 months painstakingly label each of these. So we have, one of the challenges for us in this particular discipline in flood mapping is ground truth information. So this was a very painstaking process for an expert to do, but it did provide us some way of qualitatively evaluating how we do against some of the other sort of methods that people have used for these kinds of problems. So as you can see, we are using MLR-MCL within this particular broader framework that we call HUG-FM. And it does quite well compared to the state of the art, including, for example, Planetoid is a neural architecture, semi-supervised learning neural architecture. SVM can be thought of as a single layer perceptron, again, a neural architecture. And then some of the existing efforts from the remote sensing space. So we did a comparison with them. And importantly, since I did touch upon scalability, this is something that's important. When you talk about human machine teaming, you often want sub-second latency as a criterion for effective teaming. You don't want the human to be waiting or the domain expert to be waiting unstintingly for a very long time to get a reaction from the machine agent or the system. And what some of the different scalability operations we have with an MLR-MCL does is it does deliver back at the sub-second latency, which is usually important for these kind of human-machine teaming exercises. In general, across a range of problems, not just image segmentation, but social network analysis, chip design, the software is being used by Intel inside some of its CAD machinery as well. So it's widely used in several different areas. But in general, we find that some of these optimizations can give you anywhere from 2 to 3 orders of magnitude improvement in scalability. So I'm gonna essentially stop here. There are sort of the take homes that this talk kind of covered. Again, as I said, I haven't worked in pathology, but I'm very interested in learning from some of the problems you guys are describing. What I talked about is a method that essentially simulates stochastic flows or random walks and uses that to cluster graphs. I tried to show you how such things can be useful for image segmentation problems, such as some of the things that several of the speakers before have talked about. The importance of being able to scale these things at sub-second latencies is critical and related to the talk that Eric just provided in terms of human-machine teaming. And so the high-level question I have right now is, can we employ similar ideas in the pathology context? So I'm going to close at this point. And thank you for your attention.
Yes, Srini, thanks for the insightful talks. In fact, I posted a note to the chat asking people same question as you just asked, saying how some of these techniques can be useful for the pathology images or data sets. Does anybody have any question or discussion? We have 5 minutes. We can use for different questions and discussions.
So I had a question, Srini. How do you, when you think about pathology data by itself and the sheer magnitude and the size, do you think, is it realistic to apply those broadly to pathology?
Yeah, no, in fact, Anil, that's a great question. I think, yeah. So when I was, looking at, some of the images that David and showed me from your lab, as well as some of the images that Lee has talked about. So some of these images that we are dealing with are roughly at the same scales in terms of, when you're talking about, billion node graphs, or in fact, in our case, we've applied this for tens of billions of nodes. So they can easily be adapted to the scales of data that we are dealing with in sort of the pathology example, but on a per image basis. But then I think one of the big challenges that I see is that pathology brings to bear, very specific challenges with respect to which regions you're focusing on in your evaluation, in your pathology report. And that's not something that um, uh, these general purpose tools are going to be able to do. Now, when we looked to sort of applying or using this tool in the flood mapping exercise, there were certain areas that these experts did focus on. And so leveraging that expertise and inculcating and embedding that expertise into the process was essential for making these things more effectively utilizable in that particular domain. And so I do think there is a bridge, or a chasm, rather a chasm that we need to bridge in order to achieve that in the context of pathology as well. And I think Raghu also talked about some of those in his talk.
Yeah, I'm also wondering about not just one-dimensional or two-dimensional data. I'm thinking about disciplines within pathology like cytology, neuropathology, hemopath, where you're looking at smears, you're looking at 3D clusters, and like you're thinking of Z stacking, where you're looking at 30 gigabyte images. So I think like it makes me dizzy thinking about the storage requirements clinically, but I cannot imagine the magnitude of computing power that would be needed to achieve such type of processing.
Yeah, no, and it also brings to bear interesting questions from the. I think you're spot on, but it also brings to bear interesting questions for how these sort of. So right now, the description I've given you, we talked about flow, these random walk based approaches for essentially homogeneous graphs. But the minute you start, stacking these into sort of related but not exactly corresponding, perhaps in some cases, you're starting to get into the realm of multi-network analysis. And that is something that several of us are looking at very carefully, both from the perspective of you know uh, uh, where you have, I mean, how does, when you start thinking about flows that sit across different networks. One thing we're looking at in the flood context is, for example, you have a transportation network, you have a power grid network, you have a water network, and you have a network. If something breaks in one, or something stops working in one, what are the downstream effects on the other? And so what you're describing basically sounds like one has to really rethink some of these algorithmic ideas as well, in order to bridge those kind of challenges, in addition to what you just described as um, the big data challenge there. I think those are good questions,
Um,
and
Srini, just
people
there is
are
one.
looking at some of those problems. Yeah.
There is one question in the chat, Anil. If I can read that out. What type of computational hardware is needed to get this accelerated response times? Could this be run on the desktop in real time viewer of pathology images?
Yeah, one of the things we're trying to do in general is um, improve our ability to democratize these solutions. And so that means, I mean, so one of the things I described, this whole multi level scheme, is something we did with the idea of being able to um, employ and deploy on off the shelf, standard machinery that is easily available today. We also, if you have the resources, can further improve on some of these results with multi GPU systems as well. We do have solutions for some of these, but again, I do want to reiterate that Anil's question was, the question about dealing with multiple of these images together, and one way to reason about this in the graph or network context is a multi-network. And within these multi-networks, how these different algorithms are being redesigned, that is something that we are actively pursuing in my group, and others are as well. So this is still at the forefront of research, and very important questions, how to understand sort of the contextual connections across these different things. And it is also related to what Eric was talking about, when you're looking at the pathology report of a particular individual, but there are other additional sources of information that exist in the full medical record that may be pertinent to your diagnosis. And so taking all of those into account is going to be critical.
Okay.
And,
So thank
again,
you.
scalability is important there.
Then we will move to the next talk, and of course we can continue the discussion over the chat. If you have any additional questions, please feel free to post it so that we will remain on schedule today. So thanks again, Srini,
Thank you,
for the
DK.
insightful talk.